Hey there, kiddos. Welcome to your first video of the second semester. We're going to start talking about how to set up systems of equations. This is going to be your first video for this unit. All we're going to do today is set up systems and answer a couple of questions, and that is it. Starting the next video, we will start learning how to solve a system and getting answers. But today, we're just going to set them up. So definitions first. You do have a couple. All right, the first one, here it is. A system of equations is a set of two or more linear equations containing two or more variables. You need to write that down. It's going to be very important that you understand what a system of equations is. What you are accustomed to is having one equation with one variable, like x plus 2 equals 7. Now you're going to have two equations with two different variables, usually x and y, but it could be any two variables. But you have two equations and two variables, and we'll solve them similarly to a one, in a variable with one equation, but you'll see when we get there. So there are three types of systems. Before we talk about what the types of systems are, you need to write down this definition. A solution to a system of equations is the set of all points that satisfy each equation. And so it's the set of every point that makes each equation true. And so there are three types of systems that you are going to see. The first type, and probably the most common, is an intersecting system. And what an intersecting system looks like is when you have two lines that intersect like this. And you saw one of these when we did the Valentine's Day activity in class the other day, when you graphed and the two lines intersected, and that point where they intersect was the answer to the problem you were being asked. But an intersecting system, whenever you have a system that intersects in just one point, it only has one solution. And that's going to be really important because you're going to be asked in a minute to determine if something has one, none, or infinite solutions. And we'll talk about how to figure that out. But so you have an intersecting system has one solution. Another type of system is to have a set of parallel lines. And if you'll remember, parallel lines always have the same slope, and because of that, they never intersect because they have the same rate of change. And so parallel system looks like this, and the two lines never intersect, and since they never ever intersect, they have no solution because they have to cross in order to have an answer, or at least they have to touch. They have to meet somewhere. Otherwise, there is no solution. The third type is called coincident. And they look like this. It's when they are exactly the same line, and so when you graph them, they are graphed one right on top of the other. And so you have two lines, but they overlap, and so they touch from beginning to end, and so they touch everywhere. And since they touch at every single point, then they have infinite solutions. So there's your three types of systems: intersecting, parallel, and coincident. And you're going to have to answer questions here in just a minute and tell me whether something has one, none, or infinite solutions. So let's do some examples. So we're going to determine the number of solutions for each of these systems, and we're going to write one, none, or infinite. Here's how we do it. So here's your first system. Both of these equations are solved for y already, which makes this really easy. If they aren't solved for y, you have to do that first. But these are already solved for y. So in order to determine if they have one, none, or infinite solutions, I'm going to look at the slope. So for this first equation right here, y equals 2x, the slope is 2 because that's the number in front of the x. For this equation, 1/2 x minus 3, the slope is 1/2. Since these two lines have different slopes, it means they cannot be parallel, and they're also not the same. In order to be coincident and have infinite solutions, they have to be the same. Well, these are not the same. That means these are intersecting, so they are only going to have one solution. If I were to graph this, these two lines would cross in just one point. So let's do the next one. So I have y equals 5x, and then I have 1/5 y equals x plus 7. Well, this top one is solved for y. Y is by itself. The slope of this line is 5, because that's the number in front of the x. But before I can do this one, I'm going to have to get y by itself. Well, what's in front of the y is a fraction, 1/5. And to clear my fraction, I just multiplied by the denominator. So I'm going to multiply both sides by 5. That cancels out these 5's, leaving me with 1y. And then on this side, because I have to distribute, I end up with 5x plus 35. Well, now the slope of this line is 5. Now, since my slopes are the same, because my slopes here are the same, m equals 5 and m equals 5, it means that they cannot be intersecting. They won't just have one solution. It tells me that these are either parallel lines, because the slope is the same, or they're coincident lines, which means they are the same line. Here's how you tell the difference. Look at the two equations. I got 5x and 5x plus 35. Are those two equations the same? No. One is 5x, one has a plus 35. Since they are not the same equation, they cannot be coincident. So they can't be infinite solutions. That tells me that these are parallel lines because they have different y-intercepts. So this has no solutions, or none. So let's do the next one. We're going to do the same thing. So here's your system of equations. I have negative 3x plus y equals negative 1, and then 6y equals 18x minus 6. Neither one of these is solved for y. So step 1, I've got to solve for y. For this equation right here, to get y by itself, I'm just going to add 3x to both sides. And when I do that, this equation becomes y equals negative 1 plus 3x. And the slope of that line is 3 because that's the number in front of the x. Now for the bottom one, to get y by itself, I've got to divide everything by 6. So this becomes y equals 18 divided by 6 is 3, so it becomes 3x minus, and 6 divided by 6 is 1. So now I have 3x minus 1, and the slope of this line is also 3. Again, I have the same slope. So it is either parallel with no solutions or coincident with infinite. So look at the two equations. Negative 1 plus 3x and 3x minus 1. These are exactly the same equation. They just happen to be written differently. If I were to flip-flop this around, it would become 3x minus 1. Since these are the same equation, it means I have infinite solutions. So that's how you determine. You've got to get y by itself, look at the slope. If the slopes are the same, check to make sure your equations are the same, and then go from there. So now let's talk about solutions. We're going to determine if a point is actually a solution to a system of equations. And here is how we determine that. Okay, first, we have a system of equations right here. 2/5 x minus y equals 0 and 3x minus y equals 13. We want to know if this point, 5, 2, is a solution to this system. Well, in order for that point to be a solution, then when I plug these numbers in, it will make this equation true and this equation true. So I have to test them. So I'm going to take these numbers, this is x and this is y, and I'm going to substitute them in. So for this 2/5 x minus y, it's going to become 2/5 times 5, because that's what x equals, minus 2 equals 0. So I just plugged these values in. Well, now 2/5 times 5, the 5's cancel, so this becomes 2 minus 2 equals 0. Well, 2 minus 2 is 0, and since 0 equals 0, those points work for that equation. So now we have to test the second one. Same process, plug in the 5. So I end up with 3 times 5 minus 2 equals, I don't know why I put that parenthesis there, 13. Do the math. 3 times 5 is 15. Minus 2. Well, 15 minus 2 really is 13. Since 13 equals 13, it also works for this equation. Since this point checks out on both of these equations, then yes, this point is a solution to that system. So let's test another one. Let's test the second one. I have my two equations, x plus 3y equals 4 and negative x plus y equals 2, and here's my point, negative 2, 2, and I'm going to plug it in and check. So let's do the top one first. X is negative 2. Y is 2. We're going to see if I get the right answer. So I have negative 2 plus 6 equals 4. And when I do negative 2 plus 6, well, what do you know? It actually equals 4. So 4 equals 4. It does work for this one. So now I have to test the second one. Let's plug this in. X is negative 2, but my x is already negative, which means I have to do negative, negative 2, which makes this positive 2. And then y is positive 2, and it should equal 2. Well, 2 plus 2 is 4, and last time I checked, 4 does not equal 2. Since it doesn't work for this one, then this is not a solution. So let's check the third one. Here's my point. My two equations are y plus 3x is 9, and then y equals 2x, and there's my point, 3, 6. So we're going to test it with the first one. Y is 6. This time the x does not come first, so it becomes 6 plus 3 times 3 equals 9. Well, 3 times 3 is 9. 6 plus 9 is 15. 15 does not equal 9. This point does not work for this equation. There is no need to check the second one because it didn't work for the first, so therefore it's automatically a no. If it doesn't work for one of them, then your answer has to be no. And that's how we test to see if something is a solution. So now let's just talk about how to set up an system of equations. You're going to go from a word problem. We're going to write let statements, which means we're going to identify what our variables are, and we're going to write the equations. We are going to do nothing else, just write them down. So this problem, we have Robert and Quinita both bought fruit baskets at the farmer's market. The contents and cost of each of their baskets is shown below. They lost their receipts, can't remember how much the unit price of an apple and a pear is. So they want to find out how much is one apple and one pear. So my let statements, I've got to decide what my variables are. I have apples and pears. This is real easy. A is going to equal apples. And you have to do this part. You've got to tell me what your variables represent. Otherwise, you've got an X and a Y in a problem and you don't know what stands for what. We're going to let P stand for pears. Straightforward. Okay? Now, we're going to write an equation for this first picture. Step 1. Count how many apples there are. Looks to me like there are 9. So 9 apples plus 1, 2, 3, 4, 5 pears equaled $5.25. That's your first equation. Your second equation is going to come from this picture. So let's count apples. 1, 2, 3, 4, 5, 6, 7. So I have 7 apples and 4 pears. That equaled $4.10. That is my system of equations. I'm done. You are going to do nothing else with this until we learn how to solve. All you have to do. That's your answer. Done. So let's talk about this one. A breakfast menu says 2 eggs with 1 sausage patty is $2.23 and 3 eggs with 2 sausage patties is $3.76. Set up the system. So let statements first. I have eggs and sausage patties. So we're going to let E equal eggs. And we're going to let S equal sausage. Very easy. So we're going to take this first sentence. First part of the sentence. 2 eggs with 1 sausage is $2.23. So that's 2 eggs plus 1 sausage is $2.23. Next part of the sentence, 3 eggs with 2 sausages for $3.76. So 3 eggs plus 2 sausages is $3.76. That is the equation. That's how I would solve, that's how I would set it up. And I just, picked it from the problem. So let's do another one. I have a rectangular flower patch that has a perimeter of 48 feet. This part is important. Perimeter of 48 feet. I might need to choose a different color. Let's go with this one. Perimeter of 48 feet. The length of the garden is 2 feet more than twice the width. We want to set up the system of equations to determine the length and width of the flower patch. Let statements are not necessary here. They gave you variables. L stands for the length. W stands for the width. Let's start with the fact that they told us the perimeter. If you think about it, when you have a rectangle like this one surrounding the words let statements, and you want to find the perimeter, the formula for the perimeter of a rectangle looks like this. Perimeter equals 2 times the length plus 2 times the width. You have seen that before. I guarantee you have somewhere. But they also tell me that the perimeter is 48 feet. So instead of putting the P, I'm going to replace that with the 48. So that's going to be my first equation. This is the perimeter equation for a rectangle. That is the perimeter. The second equation will come from here. The length of the garden is, well, that means length is 2 feet more than twice the width. 2 more than twice the width. That's your other equation. That's how you would set up that system so that you could solve that. I'm going to tell you right now, that is not how I would solve this problem, but because they did ask us to set it up, I promise it's going to show up as a question on a test. You need to know how to set it up. And so that's where it came from. So last one. And this one is important because you're going to see several problems like this that are going to show up, and these are the toughest ones because of how they are set up and how you have to think about it. So you're collecting tickets at a football game. Reserve seat tickets are $4 each. General admission is $3. After the game is over, the turnstile count, which is the thing that people walk through, is the little round thing, and it clicks as you go through it, and it counts people, okay? So the turnstile count shows that 1,787 people paid admission. You count a total of $5,792 from the sale of tickets. You're ready to leave for the post-game date when your boss says, by the way, how many of each kind of ticket were there? Rather than spending half an hour sorting and counting all the ticket stubs, you decide to use algebra because you know how to set up a system. So set up a system of equations to determine the number. We're just going to write the system. We have two things. We have reserve seats and general admission seats. So we're going to write our variables. We're going to let X be reserved, and we're going to let Y be general. And so we're going to write this. Now, there are two different equations. There are two different things here. There is total people, and there is total money. And you have to write an equation for each. Let's do total people first. You know that 1,787 people showed up. You also know that they all were either reserved or general people. That means for my total people, X plus Y equals 1,787. Reserve seats plus general seats was that many people. Total money is where you have to now include the cost of the ticket. We know that this is the total amount, this dollar amount, 5,792. We also know how much each ton of ticket costs. So when I'm doing total money, I've got to include how much the tickets were worth. Reserve seats are $4. So $4 for a reserve seat plus $3 for a general seat had to equal $5,792. These are very common questions, and you will be asked questions like this a lot. Whenever you are asked a question like this, you always have a total number of items and total money. The only time you have to include the cost of the item is when you're dealing with the money. The other equation, you just add up the items. Okay, that is setting up systems. We will practice this all when you come to class tomorrow. Please make sure you have your notes when you walk in so that we can check you off. This is your only video this week, so it is the only set of notes that's going to count. Y'all have a good rest of your evening, and I will see you tomorrow.